Hello everyone. Here with us today is Jose Pinilla, who will tell us about minor embedding and new tricks for it. Um, please take it away.
All right. Well, hello, and thank you for having me. Yes, my talk is titled Context-Aware Minor Embedding for Quantum Annealing Processors, and this is work done uh, during my PhD at the University of British Columbia under the supervision of Professor Steve Wilton. Followed the INQA community for a while, so I wanted to share my findings with you, so I really appreciate this opportunity. I'm going to start with a breakdown of that title, which tells you the theme of the contributions of the work towards this research problem that is minor embedding, which is useful in real-world applications because it is part of the programming flow for quantum annealing processors. Now, I don't need to give you background on quantum annealing, but I will describe how I view these devices, kind of from the perspective of the minor embedding problem. So there's this graph representation and considerations when programming these devices. I'll describe what I mean by context awareness in this scenario. So in general, this means the use of information associated to the problem to guide the minor embedding algorithms and improve the quality of results from the quantum annealing processors. So what I mean by information here, or context, I have two types of it for this presentation. The first one will be layout awareness, and the second, structure awareness. So this awareness results in different ways that we can guide the minor embedding. So for the case of structure awareness, it relates to quantum-assisted machine learning specifically. So I'll also have to mention some collateral work or some things that we have to do to make things work, to make those ideas work as collateral. So I'll give you first a simple outline, beginning with some background, again, focus on the programming flow, minor embedding, and then followed by the contributions and conclusions. So why focus on minor embedding? So we're motivated by this potential speedups in many applications of quantum computing, so many, and then as one of them is machine learning, which is also an envelope for many other applications. There are two main complementary approaches in quantum computing, or models, this Gates and annealing. And annealing is a specialized model of the Ising or qubit, which makes it easier to scale regardless of the technology it's implemented in. So even though there are many technologies with functional qubits, superconducting qubits are the most common. And for example, D-Wave has built these superconducting devices with more than 5,000 qubits. So at this scale, we start seeing the need for good software tools. And this is our perspective, and it's that a quantum annealer is only as good as the software stack used to program it. And so, of course, programming is a little more complicated than just formulating an optimization problem. There are multiple steps. We're translating this Ising or qubit onto a corresponding graph. We're mapping that graph onto physical qubits. We're calculating the corresponding couples and biases, selecting how we evolve the system. And we're turning the samples that it provides back into solutions of the problem. So this is very reminiscent, and it's just as important as software and digital design tools. Maybe this is a good opportunity to say that my previous background was before quantum computing. I worked on computer architecture, tools to program FPGAs and accelerators, for those familiar with that. So you might see some of that influence in the work. So the focus of this presentation specifically is on the mapping step onto the qubit graph. So in terms of qubit graph, I referred to the D-Wave topologies, which over the years has had different designs. It's evolved in complexity, both in the maximum degree and also in the connected structures that we find in it. So it goes from Chimera to Pegasus to recent prototypes of Zephyr. So I'll also mention that manufacturing of the circuits has higher requirements to reduce faults. And even after tuning some of these components, some of the qubits may not work well. And so they can be disabled, which results in qubit faults. This is a feature that allows them to still have devices with lower yield. So I mentioned this because it means that both the problem and the device are inputs to the programming flow. So because of the sparsity of those graphs, a one-to-one mapping of nodes to qubits is unlikely, and we need to run the minor embedding. So minor embedding, it means finding the assignment of nodes to qubits or chains of qubits that form a minor of the graph. And typically, we have two ways of doing it. There's systematic and heuristics. Systematic is where we use the homogeneity of the graph to find easy or quick assignments of special types of graphs. For example, there's if I click onto a chimera, We have the assignments to rows and columns of chains, or when we want a click, we can just use some type of L-shaped chains, or there are other techniques. However, when there are faults in the qubit fabric, like I mentioned, that can't be avoided, or where we want to map something that doesn't have a special structure, we use heuristics. And this is where we make smart moves from random guesses. This works for any graph topology. These algorithms are mostly based on path search, which iteratively solve congestion or overlap. And as an example, there's D-Wave's minor-minor. And so I'm going to label these algorithms as context agnostic because in their default mode, they only take as input the adjacency of the two graphs, the problem and the device. And so I'll move to what I mean by context awareness. And as I mentioned, there are two types. So I'll start with layout awareness. So layout, I mean by that location information, which conveys locality or distance between nodes. And this can be either natural, like from the creation of the problem, or artificial, because we can create a graph drawing with some different heuristic graph drawing methods of the graph. So we propose using here a two-stage minor embedding approach, and we use something called a layer-aware global placement as the first stage, where we map nodes to sets of qubits, so one-to-many. And this is followed by a detailed routing, where we turn those initial assignments into valid embeddings. So for the global placement, we propose something called diffusion-based migration. And then we tested this idea with two different detailed routing methods. So one of them is called a disperse, where we lock initial assignments into place. And then the other idea we tried is with the minor-minor from D-Wave. So that one rips these chains and tries to reroute them every time instead of the locked approach from the disperse method. So a good way to see the difference between these is with an example. So I show here one with the embedding a grid onto a chimera graph. So the first minor embedding that I show here is without global placement, so layer agnostic. And it results in this kind of tangled chains, or also chains that are reaching around the perimeter. And we see some of that in the view of the minor embedding. And then second, if we use something like disperse method, we'll see that it locks nodes into place here. And as expected, it's very spread out because those nodes are locked. But we do get short chains with low deviation, but it's very unnecessarily spread out. And then lastly, well, that's what we call the combined approach, which is using minor-minor on top of after using the global placement. So it combines the best of both worlds. We have short chains, low variation, and this is a result of being able to move those things around, starting from somewhere smart. So the experiments we run on this were mostly comparing combined and agnostic, because it's the better example of adding layout awareness to the initialization. So we ran those two methods with different benchmarks, different types, and we had some key takeaways. So adding layout awareness on average will result in embeddings results 19% faster. Some other metric was the success rate, just being able to find an embedding given some time to the algorithm. There's a really high increase here from 23 to 48% or 93 to 100% about adding layout awareness. And then in terms of chain metrics, so chain length, just when we measure the result of the embedding, we have 16% lower maximum chain length and 3.6 lower average. And there are other metrics that we could look at. Some important ones, there's the number of interactions and things like this. But all of these are important because of their impact that they have on the energy, which is where we really care about, just like the behavior, the performance of the device when we actually take samples. So we run those different embeddings of those problems on the D-Wave machines and look at the energy depending on chain metrics. In this case, average chain length here on the x-axis. So I wanted to talk about this example in particular, which is a graph that doesn't have a natural layout information. We just create one from a spring layout, but the problem has some locality information. Then as a result, we found that layout aware had higher success rate, have found it faster, and with this better quality embeddings, they translated into 13% lower average energy, which is really good results for performance of the device. So we interpret these numbers kind of as the result of the reduction of the search space. It helps us resolve routing conflicts earlier. And so adding layout awareness means we have more time to optimize the minor embedding. And we have at the end more solutions to choose from. We can pick from different embeddings if we get them faster. And this all results in being able to get better performance from the device. This is the first idea of context awareness exemplified with layout. So now I'm going to move on to what I mentioned of quantum assisted machine learning. And I also said that we had to build some things to get that going. So for this part of the quantum assisted machine learning, we had to implement a framework. So in this context, this framework needs to train both restricted and general Boltzmann machines with a quantum annealer used for the sampling part. I'll also mention that we had to fix a common problem that we found in prior work. That's called the positive phase temperature scaling. So I'll get to that after the first introduction of the framework. So I'll just give a very short background on training Boltzmann machines. Let's start with restricted Boltzmann machines, which consists of two parts. We need to implement what's called the positive phase in training, where we compute the conditional probabilities of hidden nodes just from data clamped to the input nodes. And this is kind of also called like the forward phase. In restricted Boltzmann machines, this is easy to do classically because the probability of reading a +1 from a hidden node only depends on the value of the visible nodes. Now, the second part is the negative phase, which can be approximated classically, but here we're interested in the quantum assisted version. So we transform our network into an Ising model. We compute the joint probabilities of each node from samples. And then with those probabilities, we compute the expectation values conditioned first on the data for the positive phase, and then on the model as a whole for the negative phase. So then for general Boltzmann machines, non-restricted, we have the same two parts. However, in the positive phase, because the hidden nodes are conditioned on each other, we also use the quantum annealer to sample from the clamp model. And so we compute the probabilities and expectation values from those samples, and then the negative phase doesn't change at all. But it's the same with two parts. So having those two building blocks for restricted and general Boltzmann machines, we built the quantum assisted machine learning framework. So to train a model, we sample from the two different phases, use the expectation values to compute the gradients for each parameter, and then just like in classical machine learning, we use stochastic gradient descent with those gradients and iteratively train while reporting different metrics. Now, we believe that this framework will be the first of its kind. It provides many options in minor embedding. It integrates derivative packages and PyTorch. It's all open source. There's a demo available at the link that I show here. However, like I mentioned before, there was a problem that we found in prior work. And I'm going to go on a quick tangent here just to talk about it and to tell you why it's significant. So just to go in more detail, basically the reason why we can use this derivative machines is because both the models, like the Boltzmann machines and the device, are meant to provide samples that can be characterized by a Boltzmann distribution. And this is down to a temperature factor. So that temperature here, what I call here the D-wave inverse temperature, is used to encapsulate all sources of noise, not just physical temperature. So there are methods to estimate that value. This is what we call the effective inverse temperature. So the problem we found was not in estimating it, but in how we use that estimate. And so in prior work, you would sample from the original parameters in the positive phase, and then from temperature scaled values in the negative phase. So this is the idea that they cancel out, that the estimate and the actual temperature of the distribution cancel out. In our work, we use temperature scaling. We use first sample from the range scale parameters in the negative phase. This is here the alpha value, it's the scaling factor. So you see both terms in the distribution. And then after doing that in the negative phase, we go to the positive phase where we scale with both the range scaling factor, alpha, and the temperature scale value. So here is beta effective. So we have those two scaling factors there. And so I'm going to demonstrate what the purpose of that with an example. So training for the classification task of the bars and stripes dataset, pretty simple dataset, but here the graph shows the testing accuracy over 200 epochs, classifying between bars or stripes. So each line here corresponds to a set of modules that's initialized with different seeds, each line. And each color is a different parameter range. So we initialize those values with different weight ranges. So this shows how critical it was, without using our method, to tune the weights. With models initialized with small values, gradients tend to vanish from the temperature scaling. It just gets better, like from blue to orange to green, it gets better as you reach the device range. But if you go too high, which is the red line, the parameters can overflow, and then we have to halt training, which is what happens with the red line there. So then in our work, this simply doesn't happen. When we train a model, we separate what we call the range scaling to the set temperature scaling. And this also results in lower quantization error because we're using the whole range of the device. That's really important. So this is a big change in the programming flow for restricted Boltzmann machines training using quantum assisted with these quantum annealers. So with that in mind, we use that framework with all those characteristics for these next contributions. And so this is what I call structural awareness. So structural awareness for quantum assisted machine learning. And we identified 4 properties. So the first one is that nodes are explicitly divided into visible and hidden. So they give us different purposes for those nodes. Second is that chain assignments of nodes with the same connectivity are interchangeable. This applies to any optimization problem as well, but it's just that in machine learning, we find this more often because of the symmetry and the types of graphs that we use. Then third, the graphs are typically organized in layers to facilitate computation. And then fourth is that machine learning graphs can be modified. So it's also what we call pruning in classical machine learning. And we can do this without losing overall functionality. And I'll show you more about that. So with that in mind, we use those properties to help us in embedding those models. So for example, for restricted Boltzmann machines, and here I show an example onto a made-up chimera type graph, there is a systematic by-click method. This uses the first three properties, because we use the knowledge of the layers to map onto rows and columns. We know that we can swap between chains, and we know that we can swap when it's between like the same visible or between hidden nodes. And then for the fourth one, we focused on something new, and is when we have faults in the graph, just like I mentioned before. So those faults would split the chains of qubits up to a node, and we'll split them into what we call subchains or disjoint chains. So in the literature, we found one method, or like the first earliest method from Adaption Henderson, but the method is to interpret the chains as broken and then you simply resolve them by majority vote as if they were connected. You resolve them as a single node, or of course randomly if it's a tie, or you can dismiss them. But you solve first by majority vote. But then we created a few more examples of what we could do when these faults happen. To demonstrate what happens when we prune a model. So first of all is what we call adaptive. And this is when we keep just one of the subchains. Pretty easy. You just, if it's broken, you just randomly, or you pick either one that's more connected or you pick randomly. Second, it will be one that we call priority. And this is when we can swap, for example, label nodes in classification tasks onto more connected chains, because there's some priority associated with that node that needs to be more connected. And then third, we have a method called repurpose, where we flip the row column assignment. And so this happens if we can use those subchains as individual hidden nodes. For example, doing that on this example graph will result in an RBM, instead of the 6x6 that we had initially, into a 6x7 hidden nodes. But those would be with pure connections. And so as a baseline, we wanted to experiment with the results of having this different adaption methods. So we took some of those models and trained them classically on a 64 by 64 quantum-assisted restricted Boltzmann machine. Trained them classically on a classification task, this time with the data set of the opt digits, for 75 epochs. And we measured testing accuracy as we were training, and every graph was trained 3 times. Here we corroborated that classically, pruning a model reduces performance. This is what we expected to see. And it's not only in the final result, but testing accuracy also ends up having more variation. So the more we prune the graph, lower performance and more variation. But then, however, when we're using the quantum-assisted training, we see trade-offs that are quite different. So first of all, the adaption method outperforms all of them, which shows the resilience of the model to even like this disconnected changes. This makes sense if mapping exists that allows using those subchains, and it's a good option, and it can be used in combination with the other methods. And then, as expected, with pruned models, more pruning lowers performance. I show here the number of edges that are pruned. But then this happens except compared to the bi-click embedding, which is one that doesn't have any pruning. It's just we're able to find somewhere in the device a fully bi-click graph. So that part is counterintuitive. It's telling us that smaller models are performing equally or better than the bi-click version. And so we concluded from this that pruning, informed by the existence of faults, is not only useful to improve that resilience to the faults that are in the device, but pruning should also be considered if it improves the quality of samples. And that's, for example, by having a change in the embedding. And so we wanted to test this on general Boltzmann machines as well. And so, like I mentioned, we have the same 2 parts for training. However, in the positive phase, we have to create that hidden node subgraph. And that's that graph that you see here. Do you see there without the visible nodes? And we have to do that for every single input in the data set. Now, you could naively do that and sample for every data set and wait for every input, and you wait for the samples. But that, for those of you who are familiar with machine learning, that's effectively a batch of 1. That's if you were training for a batch of 1, and that's very time consuming, very inefficient. So to make things faster, so that's the change in creating the hidden nodes graph. But to make things faster, we did 2 things with the embedding. So first, something that's called parallel quantum annealing in the negative phase. And that's been used previously in literature. It's nothing new. We embed and program the same model multiple times, and thus we have to get fewer reads. It helps with noise mitigation as well. And then second, we create what we call the batch quantum sampling. It is similar to the parallel quantum annealing, but every minor embedding has different parameters in this case. What that means is that we can have batch sizes with as many instances as we can find of the hidden nodes graph. So for example, here, if we find 84 instances, we're training with a batch size of 84. This is also an example of context awareness from the knowledge that we need samples from the same graph with different parameters. So back to our structural awareness, the only thing we don't have here is the layered graph, but we have knowledge that only the hidden nodes are mapped in the positive phase. We have knowledge of interchangeability that applies to all the nodes in a click. And that allowed us to create this batch quantum sampling. And then in terms of pruning, there's something very interesting, and is that if we can train any pruned graph starting from a click, it means we can train any graph. So there's something we hope to see in future work. We tested different topologies, but just the idea of finding the best topology is very interesting. For our work, or what we were able to do, is to implement the pruning capabilities on the framework, and we tested it on the click graphs, similar to how it's demonstrated in classical machine learning. And so for our evaluation, we train a general Boltzmann machine with different pruning ratios. Here is 70 and 80% of the weights. We were able to do this efficiently using the batch quantum sampling. We do this with the bars and stripes data set. But now we use this sample scoring metrics just because these are used in smaller setups where the testing set is small, so it's not very representative. So instead we measure precision of the trained model. So this is the capacity of the model and the sampler to retrieve images that belong to the data set, so just something that belongs. And then recall, which is the capacity of the model to retrieve representative distribution of the data set. So it gets different versions of what's in the data set. We compare here against simulated annealing as a baseline, but we know here that it's just to show symptoms of a bad sampler. And I'll show you what I mean by that with the next slides. And other classical methods will actually be very time consuming, even at this size of the model, which is 36 by 16, but pretty small. And so in the results, I'll show you first precision over 50 epochs. Each line here is a model topology averaged over different seats for the weights. It shows very high precision, classically, as the simulated annealing, but also very high variation. And even here we see with the pruning ratios kind of matching our intuition. As we prune the model, it lowers performance. Pretty noisy, but you can see the lower performance. But then when we look at quantum-assisted training models, we do have lower precision, but it's more stable. And again, pruning matches our intuition. Smaller models, as we prune them, we get better performance. But the big story is when we look at recall. So getting these representative samples of the data set. First, for the baseline of simulated annealing, we find basically no recall. And this is the symptom that I was talking about for a biased sampler. It's biased to returning the same sample every time. So this is not a good representation of the Boltzmann distribution. Now in quantum-assisted training, we find much better recall, but more importantly, the results we focus on is the comparison between those pruning ratios. And again, here, counterintuitively, the prune models have very high recall. This is a sign of better generalization from smaller models. Now, this tells us that the trade-offs in pruning for quantum-assisted machine learning are not the same as in classical. So pruning should be considered if it improves the quality of samples, for example, by having a change in the embedding. So these are very interesting results that we found. So I'll jump to conclusions. Kind of bringing back to what I meant by context awareness is the use of information associated to the problem graph to guide the minor embedding and improve the quality of results from quantum processors. And through this presentation, I touched on different novelties from our work related to types of information, to the layout, quantum assisted machine learning, and all this. And there's also novelty in the collateral, or just the things that we had to build to make things work. Of course, there are lots of different directions in the future that can be continued. I put some here where I've looked into a little deeper so I can maybe answer questions about those. And there are bigger scope exploratory directions. Here, the graph continuum is what I mean by that pruning of the click graph, so we can train any graph. And so with that, I really thank you a lot, and I can answer any questions.
Thanks. This was actually a really clear talk. I don't think I even have that many questions.
Okay, yeah.
I was curious because this is the first time I've seen side by side the Boltzmann machine and restricted Boltzmann machine. Do you know which one is better in the end?
So I run a lot of experiments of restricted Boltzmann machine, kind of because this is kind of what you find most in the literature, because it's easy, or it's very achievable. Like you can quickly train the positive phase part classically, and then you just sample things from the quantum part. But as I was doing this, I realized how you're really not sampling from the same distribution, right? When you sample classically, you're approximating with some method. So usually it's the Gibbs sampling. You just go back and forth on the network. And it's an approximation of a Boltzmann distribution. And then for the negative phase, you sample from the quantum device. So you could kind of say like a quantum Boltzmann distribution, depending on how you run the anneal, if you do like fast anneal or these tricks in D-Wave. So there's not really a match between the two distributions. So you will be able to train, but the two distributions are quite different. So I would argue more for looking more into the general Boltzmann machines, where you're sampling like the probability distribution is coming from the same model, like which is the D-Wave device. So I would argue into looking deeper into the general Boltzmann machines. I think the restricted Boltzmann machines are a good proof of concept, but I don't know how useful they'll end up being.
I see that. That's actually, I suppose, reassuring, and there is something to explore.
Yeah.
Uh, Back in the day when we were looking at applications of these Boltzmann machines, there was one person who was an expert in machine learning who was trying to convince us that there are some tasks in generative models
Mhm.
where Boltzmann machines are actually reasonably close to state of the art,
Mhm.
in a sense that people don't know how to do those particular type of generative models.
Mhm.
And even for relatively small sizes.
Yeah.
So I guess this is just a comment that it might be interesting to look into, but I don't have a specific reference in mind. But it would be
Yeah.
exciting if you could apply the same machinery for that class of problem. I don't think anybody has published that yet.
Yeah, I think that's definitely really interesting. Like everyone uh, seems to think that energy-based models are really like something to look into, and it's more the idea that these annealing devices are opening us the opportunity to do that exploration that we wouldn't have been able to do just classically. Yeah.
I see. Very well. Thank you for your time, and
Yeah.
see you all next seminar.
Great. Thank you.